In a normal life, you do not expect unexpected situations, especially if those are negatively impacting your life. However, from time to time, there are situations that we are looking for to be ordinary, unexpected, unforeseen, or unpredicted. Especially in our job profile, we are looking for those quirks, corner cases, which eventually could be shared with a broader audience. Thank you for choosing my presentation. I hope you will enjoy it. Who am I? My name is Przemyslaw Duda. The short name is Przemek, but everybody calls me Duda. I am one of the originator of not so bad CTF team down here at Intel. And above and beyond, I'm a husband and the father of 2 kids. Throughout this lecture, I want to show you or introduce the history of my security consideration, which was done in one of our products at Intel. To describe this in depth, I will have to introduce you knowledge about the HSM. We will look on it from outside and from inside. Then I will try to discuss about the disclosure process. We will finish this lecture with some thoughts and hopefully questions and answers. So let me start. HSM is hardware security module. It comes with very different flavors. It may be as small as a USB stick, and it may cost around about a few tens of bucks. It may be also server-scaled solution, which is costly, meaning it can cost like 20,000 of US dollars, and for technical support for that product, you could pay as much as 1/4 of that sum. These are the key aspects of the HSM. First of all, this is a physical device, meaning it has or should have hardware adversaries in scope in the threat models. Of course, the hardware is either defined via HDL by software, but even your secure card in the wallet runs Java nowadays. Main concept of the HSM is that it is used for crypto. Think of a device which can securely generate or erase your secret, say private key or symmetric key, which could be used then in a business for standard crypto operations like encryption, decryption, etc. Worth to note that there are 2 certifications programs, which are called FIPS and Common Criteria. The FIPS certification will be described in next slide briefly, but the key point here is that the usage of the HSM. The server-scaled HSM should be used in critical security operations, such as signing firmware update. Once compromised, the key or the sign operation would also impact the solution which you are trying to update. That's why you should use the HSM because of its security properties. Let's see how the certification could look like. The FIPS certification 140-2 has up to 4 levels of certification. The higher number means the higher security, and of course, increased amount of money you have to spend in the design and manufacturing phase of your HSM. And for instance, the level 1 certification is about using only approved crypto algorithm. But level 3, for instance, is about the fact that once you will open the device, the secure material should be erased instantly. Level 4 of certification includes advanced hardware adversaries. Think of secure cards with active shielding on the microchip, which should prevent hackers with simple focused ion beam devices from compromising the key asset, which quite often is a cryptographic key. Worth to mention that there are dozens of NIST-approved laboratories which actually perform the certification. The evaluation could last for 1 year and may cost significant amount of money. Let's see how possibly HSM could look alike from outside view. This picture shows you a sample HSM without top covering. So this is the picture from the top view. As you can see, it's quite old technology, as the HSM itself is quite old. Worth to note here that I haven't found a single particle of dust in it once I have opened it. Other fact is that it doesn't come with single screws, so you cannot use screwdriver to open it. The next interesting fact is shown in this picture. This is a switch which I call the kill switch, which actually satisfies the level 3 FIPS certification, because as you can see, here you have 2 wires which are directly connected to a device which I will show you on the next slide. And this is called intrusion detection mechanism. So as you can see, it could be quite easily bypassable. The true HSM is here. This is the system on chip embedded on the PCI Express card. One can see that we do have a battery here for servicing the kill switch. So even though you unplug the device from the current, the kill switch will eventually trigger the key erase procedure. What else could be directly seen here is that we have this metal cover which effectively removes basic skill set adversaries from the plate, because in order to hack into that, you would have to remove this metal cover first. Now let's see which HSM we will be referring to during this presentation. In our solution, we were using HSM, which was, I think, designed by the SafeNet company, which were bought by Gemalto, and then, as it occurred, Thales Group owned Gemalto. The name of the HSM is a LunaSP. It's a FIPS certified device with level 3. What's odd, so to speak, in that HSM is that it runs Java. It has the Tomcat web server to which you can actually deploy your application which implements the business logic you want to run on the HSM. So let me describe my research objectives in the historical view. First of all, my first duty was to create a threat model for our own usage. Having this document helps a lot. Soon after that, I wanted to invalidate either existing or new security objectives, since I'm a security person. And last but not least, I wanted to have a fun and profit, whereas the profit is that I can speak up to you at this very moment. During my research, I was trying to poke around the technology first. So I tried to see what could be possible found in the administrative tools which are used by so-called security officer in a highly trusted environment. So you can see the dashed box is for the trust boundary. Even though if we would find any kind of weakness here, we could not eventually say this is a security vulnerability because of this trust boundary, right? During this topic, I wasn't pursuing for any kind of vulnerability, especially I was not searching for this path which crosses the trust boundary. The main goal of this part of research was to poke around and see what are the properties of the administrative tools, as I believe was a part of the whole package. So having knowledge about security level of administrative tools, I could reason about the security level of the whole package. So I started with standard procedures. So I looked into the binary security of the tool itself. I discovered that standard procedure is that you list those security features, and you can find that there was the read-only relocation protection was not enabled, meaning after successful weakness abusing, you could override the global offset table. And then I found that, okay, the code is not position independent, so it doesn't have the benefit of the ASLR. And next, what was kind of weird to me, that there was not a single one canary protecting the stack. And also, you can see that the non-executable bit is enabled, meaning you cannot push directly the shellcode on the stack, either on the data section or on the heap. Then what you could do, and what I did, I listed the relocation table of that tool and discovered that the tool uses unsafe functions from the standard library. What was weird to me is the fact that string copy usages were okay, meaning the length of source was compared with the length of destination in all cases. I'm not sure why haven't they used safe string n copy function. Then you have this system function, which is kind of unsafe due to a couple of reasons. And I was focused on that. During the reverse engineering, I was following the bottom-up procedure. So I looked when and how the system function call is executed and discovered that weird situation in which the developers of that tool built the string at runtime and then executes the command, which looks like following. So if you would find the part of the string marked here as in the red color, if you could control this, you would eventually own this process. And this is what happened actually there. But again, since this is in the trust boundary, it doesn't say you that this is the security vulnerability. Anyway, it gives me knowledge about possibly on how the whole package is implemented. So in here, I want to show you a threat model which we were using in our solution at Intel. We had this product which was cloud-based, and the main security objective was that we were not trusting the cloud service provider. And to implement that threat model, we have used this particular HSM. So the threat model is as follows. On the left-hand side, we do have a trusted boundary in which we do develop our business logic code, and then we deploy this to the HSM. On the right-hand side, you can see how it works. Upon the Java archive is deployed on the file system, it is verified cryptographically, and if it's not, the jar is rejected or removed. But if it satisfies the crypto, then the Java archive is placed in the either app storage or in the meta files. There are two separate deployment paths which we will be abusing during this lecture. So any kind of modification done by the untrusted environment, in this scenario it would be the cloud service provider, should be catched by the digital signature scheme verification. Let's see then what is the Java archive and how the signature is implemented in it. The Java archive is a simple zip file. It has interesting properties because of that. Zip archive doesn't have metadata for any kind of crypto, so the crypto is embedded into that archive. Other interesting fact is that the technology allows you to have multiple signatures done by separate organizations or developers. And what's the weirdest is that, for me, is that this technology allows you to have partially signed archive. Let's see what could be possibly done with that. The jar signature is depicted down here on this slide. On the left-hand side, we have Unsigned Java archive, which has two Java classes, Java bytecodes, foo and bar classes, which are described in the manifest file. The signed Java archive has additional two files embedded into the archive. Let's see what these contain. So the manifest contains, along the things that I will describe, the manifest attributes. Then they have these entries for each file. So the entry is composed of the dictionary in which you define the path to the Java class and the hash of the content of that file. The signature file, on the other hand, looks very similar to the manifest and has a hash of the entire entry. This procedure is repeated for all files, and the signature block is an actual signature, raw bytes, from the signature file. So it means if you will modify either manifest or Java file or signature file, then this should be catched by the digital signature scheme of JVM. Let's see how the signature is verified by using the jar signer. Jar signer is a tool which could be used in this purpose. You can see that the legitimate signed jar is verified, though it contains some warning describing wrong usage of certificates, which are not relevant here. The relevancy starts at this point. The very first line updates the signed jar with the random file, and the jar signer verifies the signature. The weird thing is that the jar signer claims that the jar is verified, and it throws a warning that say that you have unsigned portion of the archive. So I was wondering how the HSM treats this warning. So I updated the legitimate signed Java archive with static content, and the HSM executed the code. So at that time, I was sure that they could possibly not treat this warning as an error. But from static content, you cannot execute code, right? So I have decomposed the Java archive in terms of the Java bytecode and found that they have business logic code, HSM API access layer, and third-party code, which contained the Spring Boot. Spring Boot is a framework for developing web services in Java. Let's see what could be done if you have the Spring Boot. So the Spring Boot has the phenomena called annotations. These are here for the rapid defining of new HTTP endpoints by having just a new file embedded to the Java archive. So the equation is that this could work, and yeah, it worked. So the first attack was to inject a Spring Boot class in a proper place, and this allowed for a code execution, which actually invalidated my threat model in the first place. We have contacted the vendor at that time, but in the meanwhile, we were thinking about the mitigations. So one can disable Spring annotations, but as you will discover, this is not sufficient. One can also propose a self-examining Java archive executed in Spring context, but it's also not sufficient. Let's see why. So on the left-hand side, we have this signed jar archive, legitimate Java archive. Since it's a zip file, you can do this trick. You can duplicate the Spring Boot, the entire Spring Boot in your application, and test this against the HSM. So during the deployment phase, there are two stages. The first is for the storage, and this is where the Java actually verifies the signature. And at this time, you have partially signed Java archive, which HSM happily approve. Then we have this execution, and during that execution, the Java archive is extracted in the memory, and sadly for us at that time, the adversarial Spring Boot override the legitimate one. So the self-examining jar archive in the Spring Boot context is not sufficient at all. So what I have just described was the attack with patching the zip archive with duplicated entries. And so the mitigation we discovered during the considerations was that we cannot override the main class of the Java archive with that evil main class. So we proposed to have the main class which actually verifies the Java archive if it has unsigned code in it. And then if it doesn't have such anomalies, then the code executes. There was also this threat when the cloud service provider could do this, right? So if they would have the ability to execute the arbitrary code in the HSM, they could perform signing oracle attack or disclose any kind of information, perhaps perform the denial of service attack also. But there was also the other deployment path for the metadata only. It came with the similar technology and similar problem. The security feature they had is the anti-path traversal, which was here to prevent the adversarial movements by flattening the archive upon extraction. So in order to override the legitimate config file, which was deployed through this path, you simply follow the zip archive, let's say hack, by putting the evil app config file above the legitimate one. So the mitigation was, of course, to make those files flat always. We have also a failed attempts. Mostly I was trying with manifest override, and also we tried so-called self-signed Java archive. And as I told you before, the main class override doesn't work either. We have contacted Gemalto in 2019 and Oracle as well. Gemalto had following comment for us. I will let you read this comment so you could have your own feeling about this. And after I have described this situation to my teammates, I remember this because this was funny. Because, one of us was sitting and it was like, hey, this is Java problem. No, it's Gemalto problem. No, it's Spring and our problem. No, it's Java problem. At that time, we were not sure. By now, I think that none of those parties made a mistake. The problem here is that the security of that solution is an opt-in. And this will eventually explode everywhere as long as we do security as an opt-in. The insecurity should be an opt-out if you are willing to. That would be all from my side. If you have any questions, please have a time for that.